All right, so in this video, we're going to talk about continuity of functions of two variables, and we're also going to briefly talk about limits for functions of three variables. It's so brief, I can't put it in its own video, otherwise it'll be like a 30-second video. All right, so the definition of continuity for functions of two variables or three variables is very similar to that for functions of one variable. A function f of xy is continuous at a point a, b in its domain if the following conditions are satisfied. So one, f of ab have to exist. Sorry, grammatically correct, f of ab has to exist. Two, the limit as the point xy goes to the point ab of f of xy has to exist. And three is, of course, the limit as xy goes to the point ab of f of xy has to equal f evaluated at the point ab. And so let's do a quick example. So is the function f of xy equals xy over x plus y continuous at the point 1, 1? So all we have to do is take the limit, make sure that it exists at the point 1, 1. So in other words, for a function like this, that's not defined in a piecewise sense, we just plug in the values and see if it works. And that's equal to f of 1, 1, so the function is continuous at the point 1, 1. So there are a couple properties of continuous functions that we would like to talk about. So if I have two functions that are continuous at a point, then the sum or difference of those functions is also continuous at that point. If I have a function g of x continuous at a point x naught and h of y continuous at a point y naught, then the function f of xy that's the product of g and h is also continuous. It's continuous at the point x naught, y naught. So in other words, if I have a function of two variables that can be written as the product of two functions of a single variable, and those limits of those functions of the single variable exists, then the limit of the function of two variables will also exist and be the product of the two, which means that my function is going to be continuous. And in fact, we also have continuity of compositions of functions. So suppose g of xy is a function going from whose domain is some set capital D in R2 to, and whose range is some set R in the reals. Let's suppose that g is continuous at x naught, y naught, and define z naught to be g of x naught, y naught. Let's suppose f is a function from R to R. So the reals to themselves, it's a function. And let's assume f is continuous at that point z naught that is in the domain of f. Then the composition of f with g is continuous at the point x naught, y naught. So in other words, compositions of continuous functions are continuous. That's the idea. So theorem is this sort of formal statement. Idea is, what the heck did that mean? So let's show that the functions f of xy equals sine of x cubed y and g of xy, which is the quantity x squared plus y squared cubed, are continuous everywhere. Okay, so first of all, f of xy is a composition of the function g of x equals sine of x and h of xy equals x cubed y. Since h of xy is a product of functions continuous everywhere, it also is continuous everywhere. So Don't you love polynomials and trig functions? And since g, the sine function, is continuous everywhere, right? F of xy, which is the composition of g with h, is continuous everywhere. Swell. What about the function g of xy? So g of xy is a composition of the functions h of xy equals x squared plus y squared, and f of x equals x cubed. Since h is a sum of everywhere continuous functions, you guessed it, it's continuous everywhere. And since f is continuous everywhere, g, which is the composition of f with h, is continuous everywhere. And that's all there is to a continuity. So it's pretty similar to what you did in Calc 1, just that limits here are a little more entertaining to find. Finally, in terms of functions of 3 or more variables, the idea of limits and continuity, everything is the same, but in the definition of the limit, we use something called a delta ball rather than a delta disk. So for R3, a delta ball consists of all points in R3 lying inside a sphere of radius delta centered at the origin. All right, let's do an example, finding a limit. So let's find this limit. If you'll notice, we have no fractions to worry about. Everything is continuous everywhere. I mean, each of the little component functions. And so the wonderful thing about that is we just plug numbers in. So let's see, x was 2. Plug in -1 for z. Plug in 2 for x, 1 for y. And again, 2 for x. So I get, that's going to be a -12 plus 2 cosine of 0. That's a x minus z. Whoops. And copying right is such a wonderful thing. My apologies. Let's try that again. So in the cosine term, I apologize. I have 2 minus z, so replace z by -1. So when I evaluate everything, I'm going to get -12 plus cosine of 3 pi, which cosine of 3 pi being -1, I get -12 plus 2 times -1, also known as -14. And that's all she wrote for that. And so suggested exercises are there. And next time we are going to be talking about partial derivatives. So we're going to be differentiating now. All right, that's a good place to stop, so I shall.